All right, guys, we're going to get started. So this is going to be a pretty fast lecture, so no worries if it feels a little speedy. But we're going to go into ML models and applications, and a very important one called retrieval augmented generation.
So basically, like, ML is like, obviously it's like very, very popular and very, very like mainstream right now. I think like one of the things we wanted to get out of this lecture is that we just wanted to sort of dive deeper into like a specific, very useful and very powerful application of machine learning, which is retrieval augmented generation. So sort of the agenda, like how we're going to do this is we're first going to give a brief intro, just like very, very brief high-level overview of like machine learning, some terminology, and also like large language models. And then we're going to do a quick like demo where we actually build like a very simple like RAG app.
Yeah, so first we can do a very gentle introduction to machine learning. And let's start with the scenario that you're someone like Kenny, and you're an engineer, and you want to write a function that differentiates the difference between pictures of dogs and pictures of muffins. So you want to be like Kenny and say, wow, this looks like a muffin. And then when you look at the dog, you're like, wow, this is a picture of a dog. So typically how engineers do this is we have a set of inputs that we have, and we have a desired set of outputs. And what we usually do is we manufacture and code up specific rules to help differentiate between dogs and muffins. First, we find some distinguishing features, such as maybe dogs have a nose. And then we use a set of rules to predict what is the output going to be. So for example, once Kenny writes a piece of code, hopefully when he puts in a picture of a dog, it'll output dog. And when it outputs a picture, puts in a picture of a muffin, it'll output a muffin. However, this is a little tricky because sometimes it's actually kind of difficult to tell the difference between these dogs and these muffins. So what Kenny ends up having to do is write much more instructions on how to actually clarify all these differences between these blueberry muffins and these dogs. So Kenny's a little fed up, but let's say that he has a lot of data, a lot of pictures of dogs, and he has a lot of labels labeling what these pictures are. And he also has a lot of pictures of muffins, and he has a lot of data labels on what these muffins are. And instead of explicitly coding these set of rules, he makes a grader that gives feedback to a structured set of rules so that it can improve over time. So what happens is that he takes an input, and he feeds it into a set of rules. He feeds it into the set of rules. And what the set of rules will output is a probability distribution on how confident it is on identifying each of these classes. In this case, it will say, I think it's an 80% chance this is a dog, and I think it's a 20% chance this is going to be a muffin. Now, this is going to be fed into a grader with the answer key in hand that will tell you how far off you were in terms of your confidence. And then this grader will give ultimately feedback to the set of rules and help make adjustments to it. So you keep training this and keep running this loop until you're very certain that this is going to be a dog and probably not a muffin. And once you feel like your model is sufficiently trained, you can remove the training portion of it. And instead of outputting the probability distribution, what you would do is you take the argmax, which is you take the class with the maximum probability, and output it. In this case scenario, you think that it's 80% chance it's going to be a dog, so you output dog. So what is machine learning? First, we have a model. This is Kenny. He's so handsome. Anyways, so generally, specifically, what we usually do in the traditional paradigm is we have a set of rules that we hard code that tries to map the set of inputs into the set of outputs, trying really hard to write the set of rules that says this is going to be a dog. What machine learning is going to do is instead of a set of rules, it's going to be called a model. And this model, what's it going to do is it's going to take a picture, and it's going to go into the model, and you're going to output a probability distribution of your confidence of what it thinks each class is going to be. And the grader, the actual ML terminology, is called a loss function. It will tell you how far off you were in each one of your predictions with the answer key in hand. And the feedback mechanism to adjust a set of rules through the loss function is known as backpropagation. So once we feel like the training loop is enough, we can remove the training loop and use something called evaluation or inference, where we take the probability distribution and take the maximum across it to output a final answer. So now we're going to move away from general machine learning and into language models. How do language models actually work? Well, instead of predicting the class of this picture, what we're going to instead is we're going to start predicting the next set of words. So the model that is typically used for language models is something known as a transformer. And what it does, it takes a previous set of words and tries to predict the word that's coming right after. Not only does it look at the previous set of words, but it also has a weighting system to determine how important is each previous word. Maybe in this specific sentence, the word Tony is really important, and maybe the word 8 is really important. And this attention mechanism is what helps determine this next set of words. So using this attention, it's going to try to predict this word with a probability distribution. Maybe it thinks there's a 12% chance of being a donut, an 18% chance it's going to be Kenny, and 4% chance it's going to be a muffin. So what we do with things like ChatGPT is first we write a prompt, such as write a story about Tony's breakfast. And what the transformer will do is it will pay some amount of attention to every single word in the prompt. And then it will intake these set of words and output a probability distribution on what it thinks the next word is going to be. So in this case, the highest chance is going to be is today. So it takes this word today and adds it to the front, to the very end of this prompt. And what it's going to do is going to repeat the whole process. It pays attention to the set of previous words, and it creates a probability distribution, and it's going to try to predict the next word. It's going to repeat this process until it generates something called an end token, where it tells the generator or the transformer, say, I am done writing the sentence. So when you go into ChatGPT, this is exactly what happens. It takes your prompt, and it keeps predicting the next most likely word that it's going to be. After it predicts words, it's going to eventually generate a stop token, and your completion is finished. Now that we know how language models work on a high level, we're going to go into a specific application known as Retrieval Augmented Generation, or RAG. Basically, let's say that we ask something like GPT a question, but it doesn't know some sources of information. So the question for this example is, what type of acai bowls does Kenny eat? And we have some piece of information. We have weblab info.txt that has all the information on weblab. And we have all the information on Kenny in KennyBio.txt. How does GPT know to look here when answering this question? Well, first what we have to do is split this data into smaller pieces of information to have more denser chunks of information. Then the next step we have to do is we have to go into the source of in the data and try to look for try to have a gauge for relevancy. Which pieces of information most has to do with this prompt? In this case, Kenny likes Prudavita pliables is going to be the most relevant to this prompt. While these two pieces of information have something to do with Kenny, so they're in lighter colors. While the information on weblab has no relevancy to this question at all. Next, after we determine which information is most relevant, we want to use something called augmentation, which we take all of this and put it into GPT's brain so that when answering this question, we know to use these pieces of information. After that, we will be able to use the generation and generate an answer that is based on the ground truth. So this is something called retrieval augmented generation. You have a set data source. You retrieve the most relevant context, and you augment it into your transformer model. And using this augmentation, it'll be able to answer questions that is relevant on real data. So we're not going to go too far into step 0, but essentially what we want to do first is we take these pieces of information and we split into smaller chunks so that we are able to manage the density of the information. And for the first step, it's going to be retrieval, which is a big question. How do you measure similarity? How do you look at some set of data points and know that the prompt, how do you measure similarity with this prompt against this set of data points? It's very hard. How do you tell that weblab is not relevant to Kenny, but the things about pliables is relevant to this question? So for this, we're going to use something called an embedding model, which takes in a string and it outputs a vector representation, an array of numbers, of the original string. And why do we use embedding models to create a vector representation? Well, it turns out that when we plot these vector representations, the information that are more similar to each other are closer in vector distance in some higher dimensional space. For example, Kenny likes pliables and Kenny is pretty cool are both pieces of information about Kenny. So in a higher dimensional space, these vectors will be closer to one another. On the other hand, the mitochondria is the powerhouse of the cell, has nothing to do with Kenny. So in higher dimensional space, these vectors will be far further away from each other. So we're going to be using this vector distance, or cosine similarity, as a metric of how relevant is information from one to another. So what we are able to do is we take our set of information that we know, and we take our prompts, and use an embedding model to create vector representations or arrays of numbers. And then once we do that, we're able to take our prompt and find the cosine similarity against every single one of these prompts, every one of these data points. And what we have is we're going to have a similarity score between the original question and all of our past data. As you can see, the prompt is about the acai bowls that Kenny eats. And it's going to output somewhere between on the interval 0 and 1, 1 being most similar, and things closer to 0 as being not very similar. As you can see, Kenny likes Pruitt via pliables is going to have a higher similarity. It's going to have a similarity of 0.66. Things that just talk about Kenny are going to have slightly lower cosine similarity, so 0.7, 0.58. And things that have nothing to do with Kenny is going to score more around the 0 area. So now we have some type of metric of how do we know what information is relevant and what isn't. We have some type of metric for similarity. Next is augmentation. Once we have all the information that is relevant, once we know which information is relevant, how do we actually feed it into our model? Well, we don't actually feed it directly into our model, but we feed it into the prompt of the model, like so. And this is doing something known as prompt engineering. It's just the practice of being really careful about how to get GPT to answer your questions. So first, what we do is we have the original prompt. What type of acai bowls does Kenny eat? Then what we're able to do is add the original context back into the prompt. So we have the context, Kenny's personality, Kenny's half Korean, and Kenny likes Pruitt via pliables. Now what we can do next is add specific directions about what you want GPT to do. So you described it as an AI assistant who helps retrieve information from a database. And you can also specify other directions, as even if you don't know the answer, you can just say that you're uncertain. You can also have fun and do basically anything else to the model itself. So for this one, I'm going to make it a cowboy. I'm going to make it have a big crush on Kenny. I'm going to have it pretend like it's on the first date. It's also going to be really nervous while talking to Kenny. It also wants Kenny to talk on the first date and pay for it. It's also Singaporean. So it's a Singaporean cowboy who's in love with Kenny on a first date and wants Kenny to pay for things. So now we're going to go on to the generation step, which you just call the endpoint. And as you can see, it's not completely perfect. Oh, hey there, Kenny. Let's finally have dinner together. I've been looking forward to it. Nervously adjust cowboy hat. But there's a small problem. It doesn't mention anything about being from Singapore or wanting Kenny to pay on the first date. So sometimes what we have to do is change the prompt. Be more specific. Be sure to explicitly state that you are from Singapore and that you want him to pay on the first date. So you have to make some adjustments, but luckily, I am from the sunny shores of Singapore. I am a Singaporean cowboy. Now think of the bill. Can you pay for it? So sometimes you have to play with the prompt from time to time to make sure that you're answering correctly. So as a big high level, we have this type of retrieval system. How do we get our transformer models to be able to answer on relevant context? Well, first we have it in some type of database. And we use vector similarity to turn the prompt into a vector representation and use cosine similarity to measure it against every single one of these data points. Now, once we know that which ones are most relevant, we take maybe the top K or the top 3, and we add it to the prompt, and we use prompt engineering to generate a correct answer. What we're going to do later on is we're going to use something called vector databases, which takes care of the retrieval process for you. Yeah, so now I'm going to pass it off to Andrew to demo the augmentation app.
Cool. So if you want to take a look at the sort of like simple app that we're going to be demoing, you can find this at weblab.is/example. If you go to like the LLM tab, you'll see that we have like a simple RAG app set up. Basically, the way this is set up is that we have like a corpus of like some like fake documents. And these documents are just like used to contextualize the query whenever we query the LLM. We also have like a box at the bottom to actually make a query to the LLM. And essentially what will happen is using retrieval augmented generation, when we submit a query to the LLM, we'll essentially take like the most relevant documents from our corpus and we'll pass those as context into the query. And so hopefully the LLM will be able to generate a response that is like relevant to our question. So just for some like details, the model logic that we're about to implement is like fully in Node and Express. And so in particular, like there's no Python. So that means that this code is actually fully compatible with like the skeleton that we provided to you in the repo or like on GitHub. And so if you're interested at all in like implementing some kind of like retrieval augmented generation setup in your like projects, this is actually this code. You might find this code like helpful. So in terms of like the specific technologies that we're going to be using, so for our vector database, we're going to be using Chroma. So as Tony said, we need some way to store the embeddings of our documents. Remember that embeddings are just like the vectorized versions of the words or like the paragraphs that are the documents. So we're using a vector database called ChromaDB. There are lots of alternatives. There are lots of great vector databases online. For example, like Mongo even has its own vector database. Redis also has a great vector database. So if you're interested in looking into like other like alternatives, these are great options to explore. So the LLM that we're going to be using is actually not ChatGPT. We're going to be using like Llama 2, which is an LLM that was made by Meta. Primarily the reason why is because we're not actually going to be using we're not going to access our LLM via the OpenAI API. We're going to be using another API called Anyscale. The reason why we're using Anyscale is because Anyscale API gives $10 of free credits, which basically like allows this like workshop to be possible. So basically anyone can sign up for an API key, and for the purpose of this workshop, there's almost no way that anyone can like exceed these credits. It also comes with like embedding models, which is necessary because we need some way to like translate the documents into their embeddings. Of course, if you're trying to implement like a retrieval augmented generation system in your own like projects, definitely feel free to just use OpenAI with GPT. This is just a demo to sort of showcase like the general like structure of how a RAG system might look like. So before we get into the coding, just to like clarify some terminology, the corpus is like our collection of documents. So in the image, I guess like in the UI of the LLM tab, each like row of the corpus represents a single document. And each of these documents is just used to contextualize the queries that we're making to the LLM. The vector database, so in our case, ChromaDB, is storing embeddings of the documents. And an embedding of a document is just like a vectorized version of the document. So remember that Tony talked a little bit about like cosine similarity. Basically, like this is performed with the embeddings of the documents. You can think of embeddings as just like how we allow like the models to like parse the words, because like LLMs cannot like understand the actual words. They have to like do inference with numbers. So that's why we need to like translate the documents into embeddings first. And then tokens are just like the individual words or subwords of each document. So when we say we're like tokenizing a document, all we're doing is we're just like splitting up the initial document into like its like words and subwords. So for this workshop, I think we're like pretty constrained on time, unfortunately. So if you do want to just like watch along, that is like completely okay. If you are interested in trying to also like live code along with me though, feel free to run these commands: git fetch, git reset hard, and then check out ML demo step 0. So in order for this to work, you will have had to do all of the setup steps in homework 3. The first thing that we're going to do is we're just going to like set up the config. So in particular, the first thing that we're going to do is, if you remember the instructions in homework 3, we had to set up a virtual environment. So what we're going to do now is just make sure that the virtual environment is activated. So on Mac, this is just source VM bin activate. I think there's like a slightly different command for Windows, but that's in the document. And the second thing that we have to do is we have to set up our Anyscale API key. So you should have a key that's like generated somewhere. And what you can do is, I think we have not so far like actually set up a .env file inside of Catbook. So what you should do is inside the root directory of Catbook React, you should create a .env file. And you should place your Anyscale API key using the syntax that's on the slide. So you should say like Anyscale _API _key, all in caps. like equals whatever your actual API key is, and then the server should be able to import it. So now that our config is all set up, the first thing that we want to do is we want to make sure that our embedding logic is set up. In particular, like we can't do any operations unless we have some way to convert between like the Word documents and like the vectors. Because remember that like we essentially cannot do any inference or like anything if we don't have a way to have the models like understand our documents. So in this case, if you go to rag.js inside of the server folder, you'll see on line 12 that we've declared like an embedding model. This embedding model is just like one model that's available to us via the AnyScale API. GTE essentially stands for like a general text embedding, and this is just a model that's like useful and applicable to like many different LLMs. And the syntax that we use to call this embedding model in AnyScale is like anyscale.embeddings.create. So what we can do is, if we go to this generate embedding function on line 41, we see that the generate embedding function takes in a document, and what we want it to do is we want it to spit out like an actual embedding. So since we're calling an API, like in particular the AnyScale API, we have to await, or this function must be declared as like async, and then we can use await. So using the syntax that's provided to us, anyscale.embeddings.create, the model that we're passing into the to the endpoint is our embedding model, and then the input is the document. And so this will return like an object with like lots of different data. Basically, like this return statement is already provided to us. Embedding.data 0.embedding will essentially just return the embedding that we care about. And so that's basically all we need to do for the embedding. So if you want to catch up, check out step 1. The next big step that we have to do is we have to actually implement the vector database logic. So currently, if you go to our front end, or actually before we do anything, the first thing we should do is we should make sure to start all of our services. So in particular, assuming that you're still in your virtual environment, run chroma run. Essentially what this will do is this will start up your vector database. And then in your other terminals, you can run hotloader and npm start as usual. Just to clarify what's going on with the vector database, there's some code here that shows like how we're initializing it. So on lines like 50 through 54, we're initializing like a new Chroma client. So you can think of this like client as like the same as our like front end client, and this client is essentially like connected to the service that we're starting when we run Chroma run. So Chroma run is just like a database that is specifically like it's just running locally on port like 8000, and all we're doing is we're initializing a client that like can like communicate to this database. So this client can like save documents, it can delete documents, it can upload documents, etc. And anytime you see this like collection object, this collection just refers to like the specific collection of objects in our database. So a database can have like multiple collections. It's sort of the same as like how like in Mongo you also have like collection names and so forth. So in this case, we've declared like the collection name to be kappa collection. But if you want to store like multiple collections in your like local database, you can also change the collection name. So that's just a bit of context for like how this like actually works. I think if you go to localhost 5050, we should be able to access the LLM tab now. Okay, so I see like some people have already like added some more documents. Basically, at this stage, anytime we're adding, updating, or deleting documents, we set up endpoints just so that the documents are only being like processed by our Mongo database. So what we want to do in step 2 is we want to also process it in the vector database. So this logic is going to be in rag.js. In particular, like there's an add document, delete document, and update document function, and this is going to handle the document logic for saving, deleting, and updating in our Chroma DB. So the way that, or sort of the syntax for how we can save to and from our collection is collection.add and collection.delete. Remember that collection just refers to like the collection of objects that we're storing in our database. So when we want to add a document, we just do collection.add, and it takes in a list of IDs, so we can get these IDs with like document._id.toString. So one thing to note here is that this .add function actually supports adding like multiple documents to the database. So that's why we have it in like a list format. For our purposes, we're only adding, deleting, and updating one document at a time. So in order to get the embeddings and the document info themselves, I guess the document info themselves, we have them. This just refers to like the text corresponding to the document. So this is like document.content. And then the embeddings we can get from the function that we just created. So remember that generate embedding is an async function because it's making a call to the AnyScale like API. In order to like use their embedding function. So remember that document.content like stores the actual text of the document, and then we can pass this embedding into the input of our like collection.add. So to delete a document, it's very similar. Just the difference is that instead of taking in an entire ID, or an entire document, we're just taking in the document ID. So collection.delete. This delete function only takes in like IDs as inputs. And so one thing to note, or I guess one thing that's like sort of important, is that our vector database is not only storing the embeddings, it's also storing some other like meta information, like the IDs of the documents and also the contents of the documents. The reason why this is important is because when we eventually want to make queries to this database, like Tony mentioned before, we're essentially like comparing the cosine similarities between like the embedding vectors. But after we like know which embedding vectors are like the closest to our like query embedding, we want to actually be able to like extract the content of the embedding vectors that are like very close. So that's why we also have to store like the document content themselves. The last thing we can do is update document. So to update document, we can sort of do like a hack. We can just like delete the document and then re-add it. And so that's pretty much all we need for like handling the vector database logic. There is some like more logic for like in API.js. We want to also like call these functions so that when the user clicks the button, it calls these like it actually calls these functions to update the vector database. I think to save some time, I'm gonna skip this part. But if you want to catch up, you can check out step 2. And in step 2, we're actually implementing the RAG pipeline. So, or I guess in the next 2 steps is when we're implementing the actual RAG pipeline. So for step 2, we're going to focus on like querying the database for the context. Now that we have our vector database with a bunch of documents, we want to be able to query it for like the nearest or like the most relevant documents. And in the last step, we're going to take the context that is returned from this like query, combine it with the original user query to formulate like a full query prompt. And then after we have the full prompt, we'll query the LLM, and then hopefully we'll get like a reasonable response. So just to break it down, we're still working in rag.js. We now have a new function called retrieve context. And this is a function that takes in the user query and also like an integer k, where k represents the number of like relevant documents that we want to return. So the syntax for this is I guess like what we can call them like results. So collections.query takes as input query embeddings and the number of results. So we know the number of results is k because it's passed in as like a function, as an argument to our function. To get the query embeddings, remember that we already created a function called like generate embedding. So let's say query embedding is the result of this function where we pass in the string query. And we can just pass in the query embedding like that. And then finally, we want to return results.documents. So remember that like each item in the collection has like multiple different like keys, like an ID and also like the embeddings themselves. But in this case, we only care about the documents. So if you want to catch up, check out step 3. And okay, so we're almost done. Basically, now we have a way to get context. Now we just need to formulate the full prompt and query the LLM. And then in step 3.2, we'll also be like producing the final response. So I guess we're still working in rag.js. You'll see for step 3.1, we want to like fill out the messages part of this like prompt. So just to give like a broader like context, this is the chat completion function. The chat completion function takes in the query, the original user query, as well as the context that we just generated from like the previous function that we just implemented. And what this does is it makes a call to AnyScale. Remember that AnyScale is like how we can talk to our LLM. So it makes a request to AnyScale with like this like prompt and returns like a message. So if you look at the slides, sort of like the way that we structure the messages is there are different types of like roles that we can assign to each message. So when you're talking to an LLM normally, your role you assume is like the user role, and the LLM assumes that the user is like the person that they're talking to. On the other hand, you can also pass in messages that are like that have like a system role. In this case, the LLM knows not to like respond to the system role, but the system role is more to like give context to the LLM, and it's more to tell the LLM like how to behave or like how to act. So we have like a base prompt given to us here, and we're going to pass this in as like a system message to the LLM, so it knows like how it should behave essentially. So if you look at the base prompt, it ends with like, you are given the following context to help you answer questions. So this will like, we'll be able to like concatenate the context at the end. And then finally, we want to pass in like the user prompt, which just contains the query. Because this is like, the LLM is assuming that they're like talking to the user. So we want to like pass in the user query. There's some other parameters here, like the temperature. Essentially, this just controls like the variance of the LLM's response. And then we're basically done. We've implemented everything that we need. All we need to finish up is like implementing the full like pipeline. So this is a function called retrieval augmented generation. We're still working in rag.js. And essentially, what this function does is it takes a user query and just produces an LLM response. So remember that the first step in producing a response is to get the context. So we can use our retrieve context function. And remember that retrieve context takes in an integer k, which is like the number of documents that we want to query for. This can be any number that you want. We've defined like a constant num documents to be 2. But it really doesn't matter. And then finally, we have a way to get a response with this like chat completion function. And then finally, we can just return the response. So just to give context for like how this function is being used, if you go to api.js, you'll see that like in this post request / query, this is where we're actually getting the response. So when the user makes a query, like at the bottom of the screen, they press enter, it makes a post request to this like to this function here. And essentially what's happening is we're passing the user query, so rect.body.query, into this function that we've just written, and this will like produce like the response. So if you want to see like what this looks like when it's fully done, you can check out ML demo complete. And we should have everything we need. In particular, like if we do like, so we have a bunch of documents. Let's say like, what food does Tony like? And like you can see like, there's one document in the corpus that's like Tony likes potatoes. So it can see that like the LM is able to respond that Tony likes potatoes. And just to like verify that like our document modification is working, we can change this to like Tony likes strawberries or something. So it's updating the document, and then if we query the model, then you'll see that like it updated its response. So this is like pretty cool. I guess like some few like concluding thoughts. In terms of like how to deploy this, it's actually like very straightforward. I think in the next lecture that we're about to do, we'll talk a little bit about like deploying your app regularly. If you're interested in setting up like a RAG pipeline with ChromaDB the same way that we have in this like demo, you can actually deploy like very easily. And if you're interested in that, you can definitely feel free to talk to like any of the staff. And finally, like one last takeaway, I think if there's anything that you should take away from this like from this workshop, it's that like RAG is like very, very powerful. I think we were able to take like any like general purpose LLM, and we're able to like make it an expert on like what is Tony's like favorite food. I think like if you can expand this to any domain, it's like a pretty powerful thing. So hopefully this gives you guys some like inspiration for your projects. I think it's like something that Tony and I are definitely like very interested in. And if you want to like learn more, definitely like feel free to talk to us afterwards.
Yeah. We noticed in your project pitches some of you guys had like recommendation systems that you guys wanted, or some type of search systems. Vector similarity search works even without the large language models attached to it. So if you wanted some new version of suggesting new things or finding things or looking for relevant information, vector similarity is also a powerful tool within retrieval augmented generation. I also attached a small demo if you want to see on Google Colab of turning strings into the vector representations and running cosine similarity across all of them to see how they actually work.